Alright, hey guys. So today we are going to be talking about trigonometric integrals, which is 7.2 out of the Stewart book. And it comes right after integration by parts for a reason. Trig integrals use kind of integration by parts or use substitution to take different powers of trig functions and integrate them. So the first case we're going to look at is where we have something in the format of sine of x to the m cosine of x to the n dx. Okay, and so this we're going to kind of go through some different tips and tricks that help us to integrate something like this. So the first case of this we're going to look at is the case where if n is odd, so that would mean we have cosine to an odd power. So if that is the case, then I can write n in the format of 2k plus 1, because that's just our generic index odd number. So 2k would be an even number, because anything multiplied by 2 is going to be even, plus 1 makes it odd. So it's just our generic odd number. And the idea here is that we're going to be pulling off a cosine. So I could rewrite this thing as sine of x to the m cosine of x to the 2k plus 1, which then I can rewrite as sine of x to the m cosine of x to the 2k times cosine of x dx. So I just separated the 2k plus 1 into cosine to the 2k times cosine, since we can do that because that's how exponents work. Okay, so another thing that's going to be helpful to us here is remembering some of our trigonometric identities. So things like sine squared plus cosine squared equals 1. And then the different ways that we can rewrite that, like cosine squared equals 1 minus sine squared, and stuff like that, or sine squared equals 1 minus cosine squared. We want to be able to rewrite things in that fashion. So what I'm going to do here with my cosine to the 2k, that's also known as cosine squared to the k. So I'm going to replace the cosine squared with 1 minus sine squared. So we have sine of x to the m times 1 minus sine squared of x to the k cosine of x dx. So from here, I can use u substitution. With u equal to sine of x, because then the derivative of u, so the du would be cosine x dx, and we get this part being our du quite nicely. Okay, and I'll show a specific example of that in a little bit, but that's the generic steps that we would take if n is odd. Then the second case that we have, if m is odd, well then m would be written as that 2k plus 1. And so we would have the integral of sine to the 2k plus 1 x cosine to the n dx. And so in this case, we would be pulling off a sine. So it's the same process, just for sine instead. So we have sine to the 2k, cosine to the n, sine of x dx. Then instead of replacing the cosine squared, we're going to replace the sine squared with, since we know sine squared is equal to 1 minus cosine squared. That's the other way that we can have that identity written. So that would be the integral of 1 minus cosine squared to the k, cosine to the n, sine x dx. Then we would do the same kind of thing. We would u substitute, and u in this case would be cosine. And then du would be negative sine x dx. And then you would go through and solve that using u substitution. Okay, so we've talked about the cases where n and or m are odd. What about the case where m and n are even? That's where we have to go through and start using half-angle identities or some other identities that we want to be aware of here. So we can use half-angle identities like sine squared x equals 1/2 times 1 minus cosine of 2x, or cosine squared x equals 1/2 times 1 plus cosine of 2x. So we can use those half-angle identities, and or this other helpful identity, sine x cosine x equals 1/2 sine 2x. Anything to reduce the power of cosine or sine so that we end up with a case that's easier to deal with, like where one of the numbers is odd. Okay, so that's one kind of situation here. If you have sine times cosine and they both have a power attached to them. The other case that we are going to look at is if we have something similar to this, but instead with tangent and secant. So this is kind of going to be a separate deal. We'll actually grab a new piece of paper for that. So this is the integral of tangent to the m secant to the n dx. Okay. So we're going to go through some similar cases here. So the first case, if n is even, then I can write n as some number 2k, because that's our generic index of even numbers. So we get the integral of tangent to the m secant to the 2k x dx. Okay, so this is where things are going to look a little bit weird. I'm going to rewrite this as tangent to the m of x secant squared to the 2k minus 1, or sorry, not to the 2k minus 1, just to the k minus 1, times secant squared x dx. Okay, so these two things are equivalent because I've subtracted 1 here, but I've also multiplied by secant squared. So this is kind of what balances that out. And the reason that I did this is so that I can use my trig identities to rewrite again. Secant squared is equal to 1 plus tangent squared. And then we can use u substitution here, with u being tangent of x, since the derivative of tangent is secant squared. So that's the case if n is even. Then we're going to go over the case if m is odd. That means I can write m as 2k plus 1. So I'd rewrite this thing. We have tangent to the 2k plus 1 of x, secant to the n x dx. So then I can rewrite this as tangent squared x to the k secant to the n minus 1 times secant times tangent. Because the idea here is that we want to get a secant tangent because the derivative of secant is secant tangent. So I'm trying to pull this off in any way that I can so that I can get this to be my du here. So that means if I subtract 1 here, I can multiply by a secant and not change the value. And then I'm pulling off one of my tangents from the k plus 1. It's now over there with the secant so that it can be my du value. Okay, but before we use substitute, we do need to make it so that this is written in terms of secant instead of tangent. So we know that tangent squared is equal to secant squared minus 1. And now we could u substitute with u being secant and du being secant tangent dx. Okay, so now we've kind of got all of these patterns for us. Now we want to make sure that we can actually do something with these. So I will go over an example of one particular case of this, which should help us kind of get the rhythm of how these tend to go. But also helpful are some other identities and also reminding ourselves of some trig integrals in general. So before we go off and do an example, I'm going to remind us of a few different integrals and identities. So first we need to remember the integral of tangent is equal to the natural log of secant plus c. And the integral then also of secant is equal to the natural log of secant plus tangent plus c. And then some other helpful identities might be sine A cosine B is equal to 1/2 times sine of A minus B plus sine A plus B. And then sine A sine B is equal to 1/2 cosine A minus B, not plus, minus cosine A plus B. And then cosine A cosine B is equal to 1/2 cosine A minus B plus cosine A plus B. So those are some also other potentially helpful identities that we could be using when we do integrals with different powers of trig functions. Okay. So those are some other possibly helpful things. Okay. So here we go. Let's do an example of how a problem like this might actually work out with our u substitution and everything. what if we had the integral of sine squared x cosine to the third x dx? Okay, well this is the case where if it was written in the format of sine to the m cosine to the n, this is the case where n is odd. So the thing on cosine, the power of cosine is odd. So that means we're going to be pulling off a cosine when I rewrite this. So we're going to have the integral of sine squared x cosine squared x times cosine dx. So all I did was split apart the cosine so far. Then I want to replace the cosine squared with 1 minus sine squared, like in our identity. So we have sine squared times 1 minus sine squared cosine x dx. Okay. Then we're going to u substitute here, where u is sine of x and du is cosine of x dx. Alright, so we're going to u substitute this, so we have the integral of u squared times 1 minus u squared du, because that takes care of my cosine x dx. Then all I have to do is distribute this u squared in. So we get u squared minus u to the fourth which then I can integrate there to get, or I could integrate that separately, or we can just integrate right where we are here and get 1/3 u to the third minus 1/5 u to the fifth plus c. But then we get, back substituting our sine of x for u, we get 1/3 sine of x to the third minus 1/5 sine of x to the fifth plus c for our final answer there. So again, to go through those steps, first we pull off a power of cosine because that's the one that was odd. Then we replace the cosine squared with 1 minus sine squared. We u substitute with u being sine. We distribute through, we integrate with the u, and then we substitute the u back in. And that's how a lot of these ones are going to go. So that's all for this lesson. I will post some other example videos as well if you would like to watch more specific examples. But yeah, that's all we got for trig integrals. Have a good one.